Actually, some interesting examples of how to read a printed circuit board. This one doesn't have a silk screen, which is an interesting. Oh, good plan. This one does not have a silk screen. This one does. If you look closely, you'll see that there's white writing all over the board. That writing indicates what type of part each one of the parts on this board is. So resistors are marked with things like R6 or R5, where R means it's a resistor, and then the number is just to make the identifier unique for when they're talking about the board in the plant. This is useful because there are some parts that are so small. If you look closely, there are some here, like those little tiny things right there. Some of those resistors, some of them are capacitors, some of them are even microchips, like these little black things. And without the silk screen, it's hard to know if they're transistors, microchips, or what. Another useful thing about this is that sometimes they will print what missing functionality is on the board. I have a router at home that has holes in it and a sign that says USB 1, where there could have been a USB connector, but there isn't. So in theory, I could figure out what parts were needed to make the USB work and then add my own USB connector to the device.
Now, this router in particular has the RAM on the back of the board here, but it has empty pads on the front of the board here and here. And if you're capable of adding your own RAM chips, it's a very difficult hack, but you could expand the RAM on this from 8 megabytes to 16 megabytes and double your capacity of what custom applications you may want to run on it after reflashing it.
Another aspect of reading circuit boards is to look at the traces, which are the very fine wires built onto the board via usually a chemical etching process. Generally, thick traces means it's carrying a lot of power, so that's usually coming from the power supply circuitry. If you're not interested in modifying the power supply, it's good to know where it is so you know what not to look at. Thin traces generally are carrying signals and are made thin just to make the board tighter, to put everything closer together.
Another thing about power supplies is when you're dealing with consumer electronics and your board has a lot of peripherals, your power supply that came with that board may not be able to handle the amperage to drive all of those all at the same time. Because in the cost-cutting process and board revisions, they may reduce the cost of components and decide, well, we're never going to be using all of it at the same time, so we can design it so that it's impossible, and you can actually damage your equipment if you were to write firmware that did that.
One of the probably last but by no means least is what the parts are and what they do. Generally, most places leave the parts with their manufacturer labels. Sometimes they sandpaper them off to try to prevent reverse engineering. If the labels are on the chips, Google or Octopart.com will usually help you find data sheets for the individual parts, which explain what the signals coming out of the part are, how it reacts to various temperature changes, its current consumption, all sorts of basic information about the chip. The problem with this, though, is that some manufacturers do not release their data sheets unless you've signed an NDA, or they don't release them, period. Generally, the smaller manufacturers do this because the bigger manufacturers would sue them. Companies like IBM or Intel maintain enormous patent collections, whereas smaller companies will try to go trade secret rather than maintaining patents. At least this is the case in the US. I'm not sure how it works elsewhere in the world, but I suspect that there are similar rules regarding how... I'm informed that the rules are very similar. That if you build a chip that replicates the functionality of another chip too closely, you could be liable for intellectual property violations. To prevent the bigger companies finding out that they've duplicated their functionality, the smaller companies simply don't tell anyone how anything works. That could be a problem if you're a hobbyist looking to get this information, because they don't want to deal with you, that is to say, give you an NDA, assign somebody to work with you, that sort of thing, because you're maybe going to buy 3 of their parts. You're not doing a production run the way a major corporation would. It's useful to be able to recognize common subsystems. One thing that if you look at this, could you get the camera up here? If you look at this board, you see some fairly large components over in one corner. In fact, you can probably see these without the camera. Generally, large components are your power supply. Big capacitors, big inductors. Let me pull them up here. That right there is an inductor, and this one and that one are capacitors, and they're large because they have to be. They're handling all the power for the entire device. That one is just large because it has most of the silicon in this device is on that chip. That controls all the routing, does everything else that the chip does. The wireless chip is this one over here. The way that I actually recognize that one of these is wireless and the other one is the routing chip
Here,
is
why don't
that
I hold this up and you point on
makes sense.
the screen?
Okay, that's a good plan. The way that you recognize that this is doing all the routing and this one is doing all the wireless stuff is that this one has traces, and you can't quite see them right here, but they're basically very fine wires going over here. And then over here, there's an inductor that goes right to the ports. So we know that this is mostly doing the routing. This has around it this copper area. On some version of this board, there's probably a shield that solders down to that for noise suppression, but this is the lower end of this router. I'm informed that if you get the high-end version, there actually is metal shielding over this, and that's just for noise suppression. The way you can figure out that this is for shielding is that that entire copper trace is all grounded, so it's to provide a solid metal shell around the thing. We can tell that this is power for a couple of reasons. First of all, there's the big components that I mentioned. If you look up some of these ICs, you'll find out that they're power regulation components. And of course, the dead giveaway is that this blob over here is the power connector. That's where it came into the board, and the traces just go straight through this area before going out into the rest of the chip, or the rest of the circuit. Whoops. Back one.
Oh, another thing to look at are the physical characteristics of the device, because that's also going to drive your design. Your basic requirements are the chips on the board, how much RAM you have, the speed of your processor. If you've got a 4-bit processor, obviously, and only a few bytes of RAM space, you're going to be programming in assembly. Some smaller micros don't even have RAM; they just have registers. And if you only have a handful of registers to work with, the only thing that you can use is assembly. And for real-time devices that do this, they'll actually count the number of cycles per assembly instruction to get the timing right. So that's when then they'll inject no ops, and it'll just be one long infinite loop. If you've got a couple megabytes of ROM and flash on the board, then you might have a real-time OS or a very, very large bare board application. Bare board applications can typically fit in under a meg of space and use anywhere from 2K to 512K of RAM very comfortably.
If you have a device and you don't know how it's communicating with other stuff, then you're probably going to need to end up reverse engineering a protocol. The most basic case is if you already have a device that speaks that protocol, and then you have the ability to basically snoop on a session. This is really useful, especially with serial communications, where they'll use a standard RS-232 for the link, and then we'll send some sort of, basically they'll pick a certain set of symbols that they want to send back and forth to indicate, do this, do that, this is the status, this is what you should do about it. And you need to know that in order to, for example, write a driver for an operating system that's not supported by the manufacturer. If you don't have something that already speaks the protocol, such as a computer that's already running the driver hardware, then fuzzing may be useful, it may not. It depends on how well the software on the device is written to handle unusual events. Because if you start throwing random data at it, it may crash or it may behave strangely. If it does either of those things, it could harm the hardware, or it could just be that you'll gain no useful information. Crashed hardware is not as easy to debug as a computer because there won't generally be an error message, it just stops. One thing that works in our favor, though, is human factors. Protocols are designed by people. When they're designing and building these things, they want to be able to debug them easily. I purchased a magnetic card reader recently, or reader and writer, rather, that communicated over the serial bus, but I didn't know what kind of communication it was, what data was sent back and forth, and I didn't have the software that I would need to run it on a Windows system and then snoop that transaction. So I needed to figure out another way to get the data out, or to get the protocol out of it. So I pulled the ROM out of it, which was a socketed chip that just stored all of the software that was used to run the thing, read it, and then reverse engineered that using typical software reverse engineering tools. It turns out that the read command is the letter R, the write command is the letter W, reset is Z, which is familiar to anybody who has used an AT-compatible modem as the reset carrier for that reset signal for that type of modem. In other words, the protocol was designed so that a person developing the software for this device or developing the device itself would have an easier time understanding it themselves, and as a consequence, anybody coming into it later would also be able to understand it easier.
Other tools are, well, BDM, depending on which configuration. BDM is in no way, shape, or form a standard. Some BDM ports are one-wire interfaces into the chip. Some are 2, 3. It really depends on what microcontroller specifically that it's connected to. You can have 6-pin BDM connectors or 8-pin as far as the pin header goes. But from the ones I've worked with, you can't dump the ROM via BDM. So if it does have a BDM port, which is mostly Freescale and Motorola chips, then there's no way to get it off using a BDM reader. JTAG, on the other hand, is...
well, BDM, have you gone over the acronym?
That's a background debug mode, and it's just a generic term that they use for debug pins on the chip. And usually you need a proprietary pod to talk with it, which is usually via USB. Sometimes it'll be parallel port or even serial based.
JTAG is another on-chip debugging methodology. It stands for Joint Test Application Group, and it's I believe 4 wires in the core of the bus that are used to send signals to the chips on a board to do things like modify registers, determine the outputs or the states of the pins on all of the chips, intercept signals between chips, read and write flash memory, which is very useful if you're loading your own firmware. It generally does not support things like single-stepping an application or modifying code while it's running. There are enhanced versions of JTAG, like MIPS eJTAG, that support that sort of functionality, but until very recently, those were not standards. They were individual manufacturer extensions to the protocol. There is some Linux support for MIPS eJTAG, but until very recently, it was entirely reverse engineered. MIPS recently released the 2.6 version of MIPS eJTAG as a proposed standard, so hopefully there will be more support for that in the future. Flash numbers and EEPROMs we'll cover in a minute. These are the pinouts of a couple of JTAG ports. The JTAG port usually shows up as a set of pins on the circuit board, and on this router, could you put the camera up here again? On this router, it's basically 12 pins right down on the front edge. But it varies from manufacturer to manufacturer. The most important lines are usually, well, there's VCC and ground, which are just power and ground, and are usually used to power a device that plugs into the board. The device looks kind of like this. That's parallel port on one end, and then this header on the other end for connecting to that. Then there's NTRST there is test reset, and the N means that it's negative logic. In other words, it's true when the pin is low and false when it's high. That resets the test port of the chip. The other reset is NReset, which is reset the full system, and it can be used to automatically reboot the device that you're testing under software control if you want to start a second test or run a long series of automated tests.
Nice thing about JTAG ports being mostly standardized between a couple configurations is you have one or 4 input pins and 1 output pin. So if you're going to try to wiggle it to figure out your pin out, it's very difficult, unlike